Hi, I'm Joe Tan. I'm a final year PhD student at the ISVR in Southampton in the UK, and today I'm going to be talking about wave-based control for non-reciprocal acoustics using an infinite array of secondary sources, and this work is in collaboration with Dr. Jordan Shear and Professor Stephen Daly. So I'll start off by giving a brief introduction of non-reciprocal acoustic devices. As we all know, reciprocity is a fundamental property that describes the symmetry in sound transmission between 2 points. So, for example, you've got an acoustic source and an observer. The sound transmission in that case is equal to sound transmission in the case when they've interchanged locations. However, this is not a desirable property in some applications, which led to significant interest to design non-reciprocal acoustic devices that can achieve one-way sound transmission. These have been typically based on the design of acoustic metamaterials, and typically non-reciprocal sound transmission has been achieved by introducing nonlinearities or breaking the symmetry using fluid momentum biasing or resonant cavities. An example of a nonlinear acoustic device is shown on the left here, where you can see a piezo patch is placed in the center between two Helmholtz resonators, which are tuned to different frequencies, and this can create the directional biasing required to achieve non-reciprocal sound transmission. In the center here, you've got an air acoustic circulator, where you've got a fan placed in the center of a ring cavity, and this creates the fluid motion required to achieve non-reciprocal sound transmission. Same behavior can be achieved using resonant cavities tuned to different frequencies, shown on the right here, where this creates the directional bias required to achieve non-reciprocal sound transmission. To further explain this concept, I'll give another example of a way of achieving one-way transmission, and that's in light. So here you can see they've got a house with a window which has privacy glass. The person in the inside can look through the window and can see what's on the outside of their property. However, anyone passing by from the outside looks in the window, the light is reflected back, and they cannot see what's on the inside of the property. This gives the ability to see without being seen. This is what we're trying to achieve with non-reciprocal acoustic devices, where you've got an exterior field and an interior field separated by a non-reciprocal acoustic device. The exterior field is perfectly transmitted and can be detected. However, the interior noise is blocked or reflected and cannot be detected. This gives you the ability to hear without being heard. As mentioned previously, non-reciprocal acoustic devices are typically based on the design of acoustic metamaterials and therefore can only achieve non-reciprocal behavior over a narrow bandwidth. This is due to their reliance on the passive resonators, and the previously proposed non-reciprocal acoustic devices have only focused on the one-dimensional case. Therefore, the motivation for this project is to investigate how broadband non-reciprocal sound transmission and absorption can be achieved using active control in a two-dimensional environment. This active control system has the ability to control the positive and negative travelling waves individually, and the advantage of this active control system is that it's fully adaptable, as in the direction of the non-reciprocal behavior can be reversed. So this is the system setup used in this work, where you've got an infinite array of dual layer control sources placed in the center, a positive incident wave going from left to right, the negative plane wave going from right to left, then you've got 4 planes of infinite arrays of pressure sensors, where 2 are placed in the upstream and 2 are placed in the downstream. On this diagram, we're also showing the positive and negative travelling waves in the upstream and downstream. These are labelled as A to D, where A is the positive incident plane wave, D is the negative propagating plane wave, and C and D are the transmitted and reflected wave components. To control the transmitted and reflected wave components individually, these wave components need to be separated from the total pressure measured at each pair of sensors in the upstream and downstream sections of the duct. This is done by a discrete spatial Fourier transform that weights the pressure measured at several sampling points. And this weighting is given here, where it applies the appropriate phase shift from the pressure sensor location to the plane perpendicular to the microphone plane. This is done by the exponential of ky, which is the spatial frequency in the y direction, and y, where the y coordinate of the location of the pressure sensor. Ky is the acoustic wave number times by the sine component of the angle of incidence. As you can see, for this system to work, you need to know the angle of incidence. From the weighted pressures, you're able to calculate the positive and negative waves travelling in the upstream and downstream section of the duct using these equations below, where it uses the average pressure between a pair of pressure sensors and the particle velocity at the midpoint. This slide shows the block diagram of the two proposed active control systems used to achieve non-reciprocal sound transmission and absorption. Both of the proposed active control systems use a multi-channel FX LMS algorithm, and in this case, the positive incident wave calculated from the wave separation method described previously is used as the reference signal for this algorithm. So the first active control system uses an infinite single-layer array of point monopole control sources that are driven to minimize the transmitted wave C. And in the second system, it uses an infinite dual-layer array of point monopole control sources that are driven to minimize the transmitted and reflected waves C and B to achieve non-reciprocal sound absorption. This slide shows the simulation results when implementing the two active control systems described in the last slide, when these systems are subject to a positive or negative normal incident plane wave. In each of these plots, it shows the transmission shown by the blue lines, the reflection shown by the red lines, and absorption shown by the black lines over frequency. The two plots on the left show the case of a positive travelling incident wave, where the two plots on the right show the case of a negative travelling incident wave. So looking at the transmission controller, in the positive incident wave case, you can see that the transmitted wave is minimized, which is the objective of this controller. However, since there's no constraint in the upstream, a proportion of the incident wave is absorbed and reflected. However, when you're traveling the incident wave is in the opposite direction, this achieves perfect transmission with zero reflection and absorption, which shows that non-reciprocal sound transmission can be achieved. Going on to the second system, where you've got the dual layer point monopole control sources that are driven to minimize the transmitted and reflected waves. In the positive incident wave case, you can see the transmitted and reflected waves are minimized, which achieves perfect absorption. However, in the negative travelling incident wave case, you see that this achieves perfect transmission with zero reflection and zero absorption. For the controller, in the negative incident wave case, since the reference signal for the feed-forward FX LMS algorithm is the positive travelling incident wave, which is zero in the negative incident wave case, these systems do not have the time advanced information required to do control, which is why perfect sound transmission is achieved and these waves are not controlled. It is also important to check the performance of these active control systems when subject to an oblique incident wave. Similar to the last slide, each of these plots show the transmission shown by the blue line, the reflection shown by the red line, and absorption shown by the black line, where the positive propagating incident waves are shown on the two plots on the left, and the negative incident wave cases are shown by the two plots on the right. Looking at the transmitted wave controller, you can see that when subject in the positive incident wave case, it's able to minimize the transmitted wave, and again, because there's no constraint in the upstream, portion of the incident wave is reflected and absorbed. However, in the negative travelling incident wave case, you can see that this achieves perfect sound transmission with zero reflection and zero absorption. Looking at the absorption controller, in the positive incident wave case, this is able to minimize the transmission reflection, which achieves perfect absorption. However, in the negative incident wave case, this system can only achieve near perfect sound transmission with some absorption and zero reflection. This is due to when you're at oblique incidence, the phase shift applied by those additional weightings in order to estimate the spatial Fourier transform. These weightings increase the pressure difference between the pairs of pressure sensors, and therefore the positive incident wave is no longer zero in the negative propagating wave case, and therefore the reflected and transmitted waves are controlled. This is also observed in the transmitted wave controller. However, in this case, the transmitted wave C is the reflected wave in the negative incident wave case. Both of these plots still show that non-reciprocal sound transmission and absorption can be achieved. This slideshow shows animations of the acoustic pressure field to help visualize how these control systems work and how the far field is affected when implementing the two proposed wave-based active control systems. These animations also show that the wave separation method has the ability to separate the spherical incident wave into its plane wave components and calculate the transmitted and reflected wave components and then control these individually. So the top left plot shows the uncontrolled case. So this is just the primary sound field created by a point monopole primary source. In the center, this is the transmitted wave controller, where the transmission is controlled. However, because there's no constraint on the upstream, there is some reflection from the control sources, which creates some wave interference in the upstream. However, when going to the absorption controller, where it minimizes transmitted and reflected waves, where the incident wave is perfectly absorbed and doesn't create any wave interference in the upstream. Going to the oblique incidence, you can see a 45-degree incident wave, spherical wave, propagating due to the primary source. Then the transmitted wave controller shows the same as the normal incidence, where you'll minimize the transmission. However, because there's no constraint in the upstream, there is some reflection and wave interference in the far field. However, because you're perfectly absorbing the incident wave in the absorption controller case, where the transmitted and reflected waves are minimized, this doesn't create any wave interference in the upstream. So here I'll briefly explain some applications for non-reciprocal acoustic devices. As mentioned earlier, this could be used for active noise control, where you want to detect an exterior field. However, you don't want to be detected yourselves, and you block or reflect an interior sound field. Another application is for full duplex communication, where you use a single transducer to transmit and receive signals on the same frequency channel. Another application is in visible sensors, where we're able to detect a field traveling in one direction. However, waves traveling in the opposite direction are blocked, so it doesn't contaminate the exterior sound field you're trying to measure. Another application is for these acoustic diodes, which could be used to improve acoustic imaging, where these acoustic diodes prevent waves traveling in opposite directions interfering with each other. So in conclusion, the proposed active control systems have the capability to control the transmitted and reflected wave components to achieve non-reciprocal sound transmission and absorption in a two-dimensional environment. And the non-reciprocal sound transmission and absorption can be achieved at normal and oblique incidence. For future work, I'd like to investigate whether non-reciprocal control can be achieved in a 2D and 3D environment using a finite array of secondary sources in a real-time implemented system. Thank you for listening. I'm happy to take any questions.